physics. So he got his PhD in City University of New York in 2008. After that, Professor He joined the University of Calgary, Canada, as a postdoc associate, and also University of California, Merced, and again go to Canada to University of Calgary to postdoc fellow, and between 2013 to 2018, he was a research scientist in University of Arkansas, USA. In 2018, he was a regular academic in la Universidad Mayor, Chile. Professor He, his research field in nonlinear optics, dynamic system, quantum many-body physics, and also in quantum information processing. Professor He published almost 16 research articles. So, for example, many articles were important. For example, one paper in Optical, 5 papers in physical letter, and over 30 papers in physical A. So this is all the research field. So today he will give the topic about the new parallelogram of the dynamics related to the radiation pressure. So please, Dr. He, continue your talk.
Okay, let me begin. Thank you for the introduction of our moderator, and thank you all for attending this talk. This talk is about a couple of dynamical phenomena in optomechanical system. Before we talk about those dynamic scenario, I gave a brief introduction of some basic knowledge of quantum and the classical optomechanical system. Okay, then we first look at what is an optomechanical system. An optomechanical system actually is a very simple setup. It consists of 3 pieces of elements. The first one is a fixed mirror, a half transparent mirror. The light can go through the mirror in both ways, from both sides. Like then, you know, if we put if a print a light, sending a light goes through it, some of light can enter the mirror, some of them will reflect it. Anyway, it must keep some transparency, a little bit transparency for this mirror. This mirror must be fixed in our setup. The second element is a movable mirror. It's something like an oscillator, mechanical oscillator. This mirror, if this mirror deviates from its equilibrium position, a spring force will bring it back to the equilibrium, just like an oscillator, like a spring. It's very simple. Okay. The third element for optomechanical system, which was very important, is an external pump. This external pump gives rise a cavity field between these 2 mirrors. A cavity field, we can say that some of the photon will be stored between these 2 mirrors to build up the standing wave, between these 2 mirrors. These fields carry an energy. Of course, it carries momentum. The momentum will push the movable mirror, make it vibrate a little bit to and fro around its equilibrium position. In this way, these 3 elements form an optomechanical system. Opto means what? It's a light. Mechanical is a mechanical oscillation. This is where its names come from. That's it. Okay. You know, one single photon carries very, very small amount of energy. So its push on the movable mirror is very tiny. To see the optomechanical effect, we must have very strong external field, much strong pump to plunge into this cavity, optomechanical, this optical cavity, which is formed by these two pieces of mirror. If our external field is strong enough, sufficient energy will be stored inside the mirror and inside the cavity, and this energy will push the movable mirror around its equilibrium position. Then we will have some interesting optomechanical effects. Okay. Okay. In mathematics, we just model an optomechanic system by two simple harmonic oscillator. One oscillator standing for the cavity field. We use A to stand for this mode. It's just the cavity field mode. The other stands for the mechanical mode, B. These two modes can be coupled in a nonlinear way. And it's very straightforward to see where the nonlinearity of optomechanics arise through a little bit of just very simple mathematical derivation. The standing wave formed between these two pieces of mirror, it has the intrinsic, so it will have some intrinsic frequency. Intrinsic frequency, expression for intrinsic frequency is very simple. Just this one, omega c equal to m pi over L multiply the speed of light. This L is just a size, the distance between the two mirrors in the original position, in the equilibrium position. Of course, that movable mirror will be pushed by the light field forward and backward. It gives a displacement, variable displacement x, which can just expand by the first order Taylor expansion, get this term, which is proportional to x. The distance, the displacement of x is the displacement of the movable mirror around its equilibrium position. Okay, after we got this element, the Hamiltonian of these two oscillator will be deformed a little bit because omega c now becomes displacement dependent. We immediately add an extra term, which is a cubic term at last. The cubic term is what? It's a nonlinear because its dynamic equation will be quadratic. It will be reduced by one order. It's quadratic. It gives us nonlinearity. This nonlinearity is very important to all the phenomena we are going to discuss, and almost all the phenomena in today's research of optomechanical system. That's it. Okay. In addition to the nonlinearity, an optomechanic system carries damping. The light for the optical field between the two mirrors, light can enter, but it can also escape through the mirror. It has damping rates. Of course, the mechanical oscillator, the movable mirror, can have some damping due to the friction. Friction inevitable in everywhere. In reality, the damping rate can be very huge. But today's technology is that to reduce the damping rate as low as possible. This is today's development of technology. Okay, so by category, an optomechanical system is a nonlinear distributive system according to the classical dynamics. Also, by the classification of the quantum mechanics, an optomechanic system is a nonlinear open quantum system with continuous variable. Due to the limitation of human knowledge, it's almost impossible to solve such a system analytically, both in classical way and in quantum mechanical way. It's impossible. For example, if we want to solve the optomechanical system, quantum dynamics optomechanic system by mass equation in the Lindebrod form, the Hilbert space will be very huge, even if we want to solve it in a numerical way, by numerical simulation. Because why? Because our pump should be very huge to see the optomechanical effect. A very huge pump will give a lot of huge number of photons. So the Hilbert space, which is classified by the photon number, will be huge. What if there are millions of billions, millions of photons. So we have billions of Hilbert space to deal with. So it's also very difficult to study the quantum optomechanics in a numerical way. Okay. Currently, most of the research about optomechanical system are based on linearization of dynamics. What is linearization? We just make a little bit perturbation. It's just like a perturbation. It's perturbation around its equilibrium. We get the equilibrium steady state and expand the dynamic system around the steady state value around it. So the system will be reduced a linear one, which is pushed by the external noise field, noise drive. It makes things much simpler. And I think there should be thousands of paper which are devoted to this way of research so far. Okay. In this talk, we're not going to discuss this part of research. We're going to have a look at the genuine nonlinear phenomenon in optomechanical system. Okay. The previous known scenario of genuine nonlinearity for the optomechanical system is only two types. One is so-called self-induced oscillation, and the other is the optomechanical chaos. If you are interested, you can check this review article in Review of Modern Physics, which was published a couple of years about some detail about the recent research. I think the research is about the last 20 years, something, not covered in very most recent year. Okay, what is self-induced oscillation? Self-induced oscillation can be realized. One external drive is Brudetune. Actually, in most of research, people use the Brudetune field by the amount of the mechanical frequency. It means that our pump field is frequency higher than mechanical frequency by higher than the cavity frequency by the mechanical frequency. So it has such a defined tuning minus omega n. In this way, there's some induced squeezing effect. Squeezing, you know, if you know something about the quantum optics, a squeezing effect is magnify everything, makes things much. It's a two-mode squeezing. One mode is cavity, the other mode is mechanical oscillator. Under this two-mode squeezing, the motion of the mechanical oscillator and the cavity field will be stronger and stronger, make everything magnified. However, due to the nonlinearity, this type of motion will be stabilized. The mechanical oscillator will be stabilized in this type of steady oscillation, like this. It's very straightforward. It's very simple to see that, okay? And by the language of nonlinear dynamics, this process is called supercritical Hopf bifurcation, or supercritical Hopf bifurcation by the people in Russia, something like that. Okay, you know, this type of bifurcation is controlled by one parameter. If the parameter is our pumping laser power, here we use square root of pumping laser power to indicate its magnitude. If the pumping laser power is very small, if we just push the optomechanical system by very weak pumping laser. If it's very weak, the cavity field will stabilize in a steady state, time independent steady, and the mechanical oscillator, the movable mirror will stabilize in standard still. However, if our pumping laser is strong enough, the mechanical oscillator will stabilize in oscillation instead of standard still. This is this phenomenon has been observed some years ago. It's somewhat connected to the dynamic scenario we're going to discuss, but it is not exactly what we're really interested here. Okay, one thing special in this kind of bifurcation that it's a steady mechanical oscillation gradually go up with the pumping laser power. it's something like a steady, a gradual transition. You see, just like a cone. The size of cone or radius cone gradually increase with this control parameter mu. It's not a sudden transition. It's a gradual transition. This type of bifurcation can be observed in many types of dynamic system. Here, it's related to one of our dynamical scenario we're going to discuss later. Okay. After this introduction, we are going to look at the first dynamic scenario we're interested. Okay. This is the ordinary optomechanic system, but the different thing that it is driven by two fields or one field with two different tones, with two different frequency elements. This is also the same as two pieces of mirror. One of mirror is movable and connect to the other mirror by a spring. The spring is a dark one, is a black one in the middle. The two fields pump into the system, build up a cavity field between these two mirrors. And this system is the same, can be modeled by the two oscillator. One of them is for the cavity field. The other is for the moving mirror, the mechanical oscillator. They are connected, they're coupled to each other by a quadratic potential, as we explained already. Quadratic potential, which is proportional to G something. It's very okay. Okay, it's straightforward to get its dynamic equation, dynamic evolution equation for this type of system. The different thing that we have two fields. See, look at the first two equations. There are two drive terms, I equal to 1 or 2. This is the uniqueness in this type of system we're interested. Okay, and the variable we use different variable for the cavity field. We use its displacement x and momentum p as two perpendicular quadrature. This quadrature can be measured by homodynamic detection in quantum optics. So anyway, we use for convenience, we just use the two quadrature for the displacement and momentum of the cavity field, and for the mechanical oscillator, the movable mirror, their x and p is just the normal definition of displacement and momentum. The one thing that, okay, look at the last equation about the mechanical momentum. The last term is what? Xc and PC squared is just a floating number inside the cavity. It means that it's just Newton's law. It's nothing but Newton's law. It indicates that the force received by this mirror will go up with the photon number inside the cavity. If there are more photon inside cavity, it will receive more forces into that. Okay, we can fabricate the system by some setup. So far, we have not done the experimental yet, but maybe later we'll try something like this. After you fabricate a system, these two mirror or the spring is fixed. They're fixed, cannot be changed anymore. The only two parameters we can change for the system is just the two things. One is the frequency of the pumping field. The other is just the power of the pumping field. We just look at how these two parameters will give some phenomenon, which are expected, which are not so expected for us. Okay. First of all, we to see how to change to see the effect of changing the frequency of the field. Okay. Okay. Of course, we can change we choose any frequency for these two pumping field, but we choose a particular one. One of the pump field is fixed with frequency redetuned by the redetuned from the cavity frequency. It means that the frequency is lower than intrinsic cavity frequency by the frequency of the mechanical oscillator. The other field is resonant. it's exactly resonant with the cavity frequency. With these two fields acting together into such a system, this system, there's something very weird will take place. Okay, if these two fields are strong enough, they exactly matched. One of the detuning is omega m, the other is detuning 0. If they're just matched in this way, the mechanical motion, this guy, the mechanical oscillation of this guy, the moving mirror, will be locked. What do you mean by lock? By locking of this mechanical oscillator, we mean that if we increase the power of the pumping field, increase the power of these two fields, increase the power within a range, the mechanical motion will be locked forward, will not be changed. See, this is a displacement of the mechanical oscillator. If we increase the pump amplitude by double time, it's the same. Its response of the mirror keep the same, no longer changed. However, if we make a little bit deviation from this matching condition, for example, like in this figure, the left figure, the first field has little bit of difference from omega. It's 1.002 omega. Then the response of the mirror will reduce to like a linear system, totally a linear. See, like this. Just look like this equation. If look at this two drive, if the drive EI increased by sometimes, for them is doubled, we have totally there'll be 4 times of external drive field. So the response of XP, XM, and PM will be increased by 4 times. The displacement XM will be increased by 4 times. It's just like a linear system. It means that the turn of the nonlinear turn G takes no effect. This is quite weird to us at the beginning, like this. Okay. If you have any question, you can just stop me. Okay, is that fine?
Yes, don't worry. I'm checking on. They can submit their questions in the chat, and if there are any questions, I will stop you. Okay.
Okay.
Thank you. Keep going.
Good.
Bye.
Okay. The second thing that we can change the power of the external fields. The power is related to the amplitude in this way, square. Here we choose that the two fields have the same power. The two fields acting onto the optomechanic system have the same power. Before we look at the effect of power within a larger range, we take a look at the mechanic motion. We get general form of the mechanic motion. Actually, for any kind of optomechanic system, its mechanical motion or its average mechanic motion without considering noise effect, but they always take this form, xm equals a sine omega t plus phi plus d something. A is the amplitude, oscillation amplitude of the mirror, movable mirror. D is a small deviation from its equilibrium position. Usually, D is very, very small, much smaller than A. In all situations, it's very in all situations. Why is there such a simple form for the mechanical motion? No matter how the things become complicated, the mechanical motion always takes this form. This is due to the resonance effect, because the mechanical oscillator is pushed by a term like this, push turn proportional to photon number, as we have seen before, this last term, okay? This term have a lot of frequency components. Only one of the frequency components with the frequency omega m will significantly contribute to that. It's a resonance effect. So the mechanical motion is always very simple, okay? So by this understanding, we can express its photomechanical energy of the mirror in this way, reduced to this way, okay? And its time average is nothing but the first two terms. Of course, D is very small. We can't just neglect that and make it like 0.58 squared is total mechanical energy. It means energy stored on the movable mirror. So much. Okay. We will use this quantity to indicate the power, the fact of the pumping power. Why we should use this power? Because it's a number. It's a fixed number. Of course, it's without oscillation. If you use oscillation like XM, there are a lot of bunch of oscillation stuck together. It's very hard to see something. Moreover, if we use this quantity to indicate our power effect, we'll see something very surprising. So let's go to the next page to something quite surprising here. Like this. Okay. What is the vertical axis? Vertical is just the average mechanical energy. This one, 0.5. The horizontal axis is just the external pump amplitude or pump power related to pump power, like this. Okay. Think that this mechanical energy can only take some discrete value, just like in this figure. See, like this figure, it only takes the discrete value. It means that what? It means that the mechanical oscillation amplitude can only take some quantized value. It's no longer become continuous. It's become quantized value. If our power become enough, become powerful, or external field become powerful enough, there could be some transition between these two different values, between the level. We call it energy level. And this energy level satisfies a power law. A power law like M, let me make it larger. See, for different energy level, it has energy proportion to M to the power 2.2 approximately. It's just only approximately. You know, for a hydrogen atom, it's have power of 1 over m squared. For the simple harmonic oscillator, quantized simple harmonic oscillator, it's have power of n. However, this is not a microscopic body, microscopic object, not atom, not electron. It's nothing but a macroscopic mechanical oscillator. It may carry a mass of nanogram or even microgram. It's a macroscopic object, but this macroscopic object also demonstrates quantum behavior. It's quite surprising to me at the beginning. See, the locking phenomenon we saw previously is just on the first level. You see, on the first level, if the E extends for a certain range on the first level, its mechanical oscillation is fixed, no longer change. It means that its oscillation amplitude changes nothing along this thing, along this horizontal axis E. If E changes from, for example, from 10 to the power of 5 to 10 to the power of 7, almost no change at all. It means that there's locking phenomenon on this first level. Okay. However, they go up to the high level. See, on the right side, one value of E. Okay, let me make it magnify a little bit. One value of E seemingly corresponding to the different value of the mechanical energy. Overlap, seemingly overlap. Actually, it's not, because we just view it with a very crude scale. If we make refined scale, make a scale that's very smaller and smaller, there's still 1-to-1 correspondence between E and EM. There are two sample magnified views on the right side. One of them is for the transition between 1, 2, 3, 4 energy level. The other is for the 5, 6, 7 energy level. If we make the scale magnified with something with a small scale, there's still 1-to-1 correspondence between the driving power and the mechanical energy. There's something very funny that if you increase the power, the transition, it's like a random transition. The transition between the level can become rather sensitive, especially if you go to the level 5, 6, 7, 8. See, the horizontal scale is 10 to -4. very small amount of change can make a transition very occur. It's also something very strange or very weird to us. Okay. In addition to this quantized behavior, on each energy level, the dynamical pattern, the dynamic oscillation are also fixed. We go to the second page. Okay, here we just plot the mechanical energy and the cavity energy. On each quantized level, the mechanical energy takes this form. So, in addition to the constant number which I've seen in the previous picture, there's some oscillation. If we look at it, if we view it by real time, we can just look at it. See, for on each level, there's a level from M1, M2, M3, M4. There is an oscillation on this energy, which is just AMD with the amplitude just equal to AMD, something like that. Okay. Most interesting is that for corresponding to each level of mechanical energy, the cavity field pattern is always fixed and with a special pattern of variation. Let's make it large. Okay. On the first level, for the first level of mechanical energy, the cavity field pattern for the half period of the period pattern only have one peak. If we increase to the second level, however, this pattern will be modified for the half of the period oscillation to have two peak. Accordingly, from higher level, it have 3 peak, 4 peak, go up forever, something like that. It's a very unique correspondence. And when I first obtained the quantized behavior for the mechanical oscillator, I just have a doubt that it could come from some numerical error. After I had seen this correspondence, I just thought that I believe that there's a physical mechanism within this kind of phenomenon. You know that if it's a computation error, it cannot be create something so how can I say that it's so unique. Okay. So there's one correspondence between stabilized mechanical oscillation and stabilized cavity field oscillation. These two things, this correspondence will exist for all energy level, something like that. Okay. Moreover, this energy level is the energy level of macroscopic body, not microscopic, not atom, not electron, but a mechanical oscillator. Okay. Let's take a look at a further example of how the system evolved to this mechanical energy level. Here, we just choose a series of external pumping power by this value. That's these two values. All these two values with a difference of something, with a regular difference, with a fixed difference, something like it. Okay. Here, the first picture is about evolution to the 3 different energy levels. The pink one and the green one evolve to the first energy level. The blue one and indigo one, deeper blue one, evolve to the second energy level. The black one and the red one evolve to the third energy level. It shows that no matter we choose this external driving power, the evolution of the mechanical motion or mechanical energy always choose this fixed position, always choose this fixed level. There's nothing between these two levels. There's no value, no result between these two values. This one, the second picture, is just a magnified view of the first energy level. We see that the average position of the pink curve and the green curve, the same. But there's a little bit deviation. This deviation is due to the very small pure displacement, which makes things more complicated. But it will not make some qualitative modification to our results, okay? Last one is about the cavity field, stabilized cavity field pattern. See, we have seen that the 2 peak, 3 peak. If we go evolve to second level, like here. Okay, sorry. Okay, sorry. Okay, I needed to make the things large, smaller. Okay, if we evolve to the first end level, the first one, the upper, it's 2 peak. It's only 1 peak. If we evolve to the second end level, the blue one and the deeper blue one, with double peak in the half oscillation period. For the third level, it's always have 3 peak. The cavity field keep the same spectrum pattern, but have its amplitude changed with different drive amplitude, just proportional to E square. It's natural to understand that because we have seen that the mechanical motion have been frozen, no longer changing with external field. The more energy input by external field will go to where? Only the cavity field. Make the cavity field stronger and strong, something like that. Okay. Okay. We're going to talk about another interesting thing. Another interesting thing is about the sensitivity to the initial condition. If the system evolves to the higher level, larger or equal to 2, the evolution process will be very much sensitive to the initial condition we choose. Here we just give an example. There are 2 curves. One of the curves evolved from the initial condition of the XPM equal to 0. The other one have this very tiny difference. The initial position of the movable mirror is deviated by a very small amount, 10 to minus 9. This XPM dimensionless one. Okay. For the real one, we need to multiply a certain factor and the real one is also very small amount. Okay. Okay. For these 2 differences, their evolution trajectory will become different. We just deviate the little bit difference in this way. The one with a small deviation will be involved to a different level, to the 5th level. If without this deviation, it should evolve to the 6th level, m equals 6. But after we add such a small difference, it will evolve to the 5th, lower energy level instead. This sensitivity even more sensitive than some of those in chaos. As it's very well known, for the sensitivity to the initial condition mostly exists in chaotic system. But this is not a chaotic system. We can make a comparison. It's totally different chaotic system, but it also exhibits the sensitivity to initial conditions. We can compare with that one type of chaotic system this way. The chaotic system is one more typical example for chaotic system is the Lorentz equation. Describe that. For this Lorentz equation, if we increase the parameter R, Raynaud, it's a Raynaud parameter, chaotic behavior will arise. We will see so-called stranger attractor for this type of system. For this type of system, the distance between 2 points, evolving points, can exponentially grow up. The distance between initially, if these 2 points very tiny, with the time passed by, their difference will be exponentially grow up, totally different. We also have the sensitivity to initial condition for all dynamic system. All dynamic system is also a quadratic nonlinear one, but the difference is that there are 2 external pumping field, which are proportional EI, the I equal to 1 and 2. Okay. For this kind of sensitivity, for all concerned sensitivity to initial condition, it's totally different. The distance between two evolving points are always bounded, because the system either evolves to this energy level or that energy level, nowhere else. It's fixed. It's always totally fixed. This one, that one. Okay. So if we make a projection of the evolving point onto the mechanical part, it's bounded. It takes the form of bounded. So this type of sensitivity is very different from the chaos. So we cannot say that it's due to chaos, chaotic property for our system to exhibit this sensitivity to initial conditions. Okay, okay. Now we finish our first part. This part was published in the last year in this paper. It's a rapid communication and physical review A. The title is a mechanical oscillator frozen on discrete level by two optical driving field. Okay, this is our recent publication in last year. Okay, after finishing this part, we're going to talk about the second dynamical scenario we are interested in. Okay, the second phenomena is about a sudden transition in a coupler. What do we mean by coupler? Coupler is a two. It means it's a two-coupled microcavity. One of the cavity carry breathing mode. Its breathing mode can be excited in a certain way. All these microcavity look like a mushroom. They grow up in the clean room in some chemical way, by some chemical method. They grow up in the clean room, just like that. Because it's there's some vibration mode on the side of this microcavity. Under some condition, this microcavity can vibrate along the radial direction, just like a breathing, just like a breathing of a frog heart, something like corazon, something like that. So if we pump it in a proper way, it will keep vibrating forever, as long as our pump continues. Okay. For this system, we model it by 3 oscillators. One of the oscillator is for the first cavity. The other is for the second cavity. Moreover, we have one oscillator to represent the mechanical mode on the side of the cavity. We know that for the ordinary optomechanical system, we have 2 oscillators. But for the coupler system, we just have one more oscillator to stand for the second cavity field. That's it. Okay. These 2 cavity fields are coupled to each other by so-called evanescent mode, because light can go out. The evanescent field can go out and couple the second one. They couple each other according to distance of between these two cavities. One of the cavity has a breathing mode. Breathing mode is still vibrating. If we keep the field, if we keep the pumping field on, it can stabilize in vibration, like this. For example, A sine omega t. Can you see that clearly? Just one of them is vibrating. The other one is rigid, something like that. The dynamical equation is just a generalization from our previous scenario. The different things that, okay, one different thing that they are coupling between the 2 cavities. The coupling proportional J. The other scenario is the other difference that we here in this process, we only have one pumping field, which is blue detune. Its frequency, the pumping field frequency is higher than the intrinsic frequency of the cavity, the first frequency by the amount of the omega n, the mechanical frequency. It's blue detune, because with blue detune field, as we have seen at the beginning, with blue detune field, we can excite so-called self-induced vibration on the optomechanical system, something like that. Okay. This type of system is real, not just exists by theory. It's a real. Previously, the science experiment realized this kind of system already, but the purpose is different. Their difference, like this one, the right one, the left one, the right one. Their purpose is to magnify the breathing mode in certain ways. If the coupling and the pump is adjusted to a good value, the vibration on one of the mushroom or one of the microcavity will be magnified, become stronger and stronger. It's called the phonon laser. It's just like the light field it's amplified in a laser. It's just like a phonon version. It's a mechanical version of laser. Two typical experiments is this one of the about 11 years ago. The other is quite a recent one. They use different way to control the magnification of the phonon field. But this process can be understood in terms of linearized mechanics. What we're interested for this phenomenon is it's a totally nonlinear one. Okay, the nonlinear one is like this. You know, for this type of system, after it's if this system is fabricated or during the fabrication, we can mostly adjust two parameters. One of them, of course, the pump field. We can change the pump laser freely. Moreover, in the fabrication, during the fabrication process, we can choose a proper distance between these two cavities, two mushrooms. We can make it larger, smaller. It will determine our coupling magnitude J, something like that. For this system, we just look at the totally nonlinear scenario for the system. The system pump the system by external driving laser. If this driving laser gradually increase from 0, one is driving is going up. If this laser's the power reach a certain amount, there will be a sudden change of the cavity field amplitude and the cavity field spectrum, in addition to the mechanical motion. It's just suddenly go up. Just for this example, if our pump power reach a certain amount E, around this point, a very tiny change of the power can make the field inside the cavity to change drastically. We just check from the left to right. Before the transition, the cavity field is a single mode. After the transition, it obviously becomes a multi-mode. Moreover, its amplitude become much stronger, right? Just like this one, that one. Because our unit is very large, 10 to 11. It's like sudden change, suddenly jump up, just like the cavity field suddenly jump up. And this jump up can be very easily detected. Very simple to detect that one, okay? How to understand this sudden transition? You know that just like in the ordinary phase transition in thermodynamics, so that type of phase transition is due to the competition of two factors. One is energy of system, the other is entropy of system. For our concerned transition, it's also the competition of two factors. One of them is the optomechanical force, optomechanical effect. The other is the mutual coupling. Of course, the optomechanical effect will be intensified by our driving power. If our powers become higher, the photon inside the cavity containing mechanical mode will be larger. Then there'll be much larger optomechanical forces to make the breathing mode vibrate more fierce. Of course, if we have the stronger coupling, if the two cavity couple more strongly, more photon will escape from that cavity and go to the other cavity. So the optomechanical force in the first cavity will be lowered. These two facts compete each other and give rise to a sudden change. A general description of such sudden change is by this phase plot. One of them is just the optomechanic fact indicated by the GM times E. The other is J. See? The color indicates the intensity of the evolved mechanical energy. We see clear-cut boundary. If the power increase, for example, increase from the C to B, if the power reaches B point, suddenly go up, sudden change, okay? And all of these have very clear-cut boundary. Moreover, this boundary is not fixed. It can be changed by the initial condition of our system. But this is relevant to initial condition, not sensitive. It's not the sensitivity like our previous scenario. This is just a gradual change with the initial condition. Okay, initial condition. For example, if we just give the mechanical oscillator initially give a push, let it carry the initial energy, the boundary will be deformed to the right one. The first one to the right one. But this bending of the boundary, the change of boundary is gradual. It changes more and more. The boundary changes to closer to the horizontal axis. If the initial energy becomes larger and larger. Here, in our example, the difference between these two initial conditions very huge. 1, 0, the other 10 to 14, very huge. The interesting for this dynamic scenario is that the sudden transition can occur at very tiny coupling between these two cavities. See here, if all j equal to 0, just for example, just look at the only one cavity. There are no coupling with the second cavity. We have seen that there will be a Hopf bifurcation. If the power of the laser go up, there is a Hopf bifurcation X at the point X. This is a gradual change. However, if there's coupling to the second cavity, even if the coupling is very tiny, the J value is very tiny, like 0.0 something, the transition around here, around X, is still sudden, very sudden. Sudden jump, it's just a sudden jump from the lower value to high value, just like you go up to a skyscraper immediately, something like that, very quick. This is a special mechanism for the coupled cavity. Very interesting, and it's also very useful to some applications. Okay, and there's some similar sudden transition in nature. Which is mostly studied in the field of nonlinear dynamics in the category of so-called the catastrophic bifurcation. What is catastrophic bifurcation? Okay. Oh, before we discuss catastrophic bifurcation, we give some more detailed view of the sudden transition. This sudden transition, how to look at the detailed view? We just make two cross sections. One of the cross section is along the vertically, from the B to C to point C to B. The other is along the horizontal line to E and F. We will see that the transition is very clear displayed with this cross section, which we saw that the transition for different initial condition occur at different place, like this. One interesting that there's no well-known hysteresis phenomenon for the process. If we fix a certain initial condition and reduce the pumper laser power, the transition point will go up. It will not stick back to the blue line. There's no hysteresis process inside that. Okay, this is a more detailed view. Okay, as I mentioned previously, this type of transition is very similar to catastrophic bifurcation in nature. Okay, so this is a catastrophic, typical catastrophic bifurcation in nature. It mostly studied for ecosystem. For example, some research points out that the Sahara Desert in North Africa turned into desert from a richer plain only within a couple of years. It's a sudden change. Or like the glacial period suddenly set in immediately. So, in the mathematical model for catastrophic bifurcation like this, it's well known. It's a condition parameter. It's condition parameter change beyond a limit. The steady state for the system jump from one steady state to another. It's a sudden jump, totally change the property of the system. Like this, see, like this. Or concerned dynamic process can be also called a catastrophic bifurcation, but there's something different. One different thing that, and or sudden transition between two oscillation. Just like a jump, if we focus on the mechanical oscillator, the moving mirror, oh no, here's not moving, just when the breathing mode, it's just jump. It's amplitude, vibration amplitude, just jump from one to another, just like a sudden jump. This sudden jump is something like atomic transition, just like a classical version of atomic transition from this level to another level. It's quite funny, quite funny to see that. Okay, the other thing that because our system is on the external drive is always stabilized. For some catastrophic bifurcation in nature, there always some unsteady state, just like the dashed one between the two stable one, dashed one. For our system, there's only the jump between two stable dynamical one. This jump is between two stable static one, or standard still one. And for our concerned dynamic scenario, it's just like the jump between always the two jump between two steady one. According to our external force, the external force change a little bit, it will jump immediately. That's it. This type of transition has some. I think because this jump is very easy to detect, it can have some important application. As far as I have known already. One example, we just give one example here for this talk. One example is to measure the optomechanical coupling constant. What is, as we mentioned before, on the single photon level, the optomechanical effect is very, very small. Why it's very small? This G, this constant is very small because it's proportional to a 0-point fluctuation. We're familiar. I think most people are familiar with this 0-point fluctuation, which appear first in the quantization of simple harmonic oscillator by this very, very, very tiny amount. So this thing, GM, become relatively small due to the existence of this small factor. Okay, although MC is quite large, this will make it quite small. Okay. Previously, the measurement of this GM, this parameter, is through an estimation by homologous detection of a noise spectrum in this paper. But it's very just roughly estimated. Given this type of sudden transition, this GM can be measured in an accurate way. Why it can be accurate way? Because we can show that this measuring process is along the boundary of this trend, along this sudden transition. As we seen in the previously and also in this picture, two things determine the transition. one of the things is GMA multiply J. The other is J. J is mutual coupling. In doing this measurement, we can choose J at a very small value, close to 0, but the transition there is still sudden, very sudden. Okay. If we also this boundary, sudden changer boundary is clear cut, and it's determined by the product of GM multiplied E. If this product change a little bit, very small amount, there will be such a sudden transition taking place. Okay. Okay, if we keep our E, the external pumping power, for the two different value of G, this product can be on the different side of sudden transition. So we can well make use of it to get the information about GM. Of course, also our boundary, our transition boundary is quite straight. It's just like diagonal one. It's a relation here for this section. The relation between this product and J is totally in almost along a straight line. So it's very easy to make use of that. Okay. Here I give you example. Put very small amount difference of the GMA, like this one. Okay. This is 10 to minus. It's in order of 10 to minus 8 kappa. Kappa is the damping rate of the one cavity. How can we discriminate it? Discriminate these two values. Okay. For the single cavity, if we only have one cavity, the response of the cavity field almost the same. They stick together, cannot change. If we add and have the addition with a second cavity, there will be some sudden change, sudden transition, as we mentioned. Okay, so these two things, these two value, the response for these two value immediately separate. So we can distinguish between these two values. These two very small amount value tend to in the order 10 to minus 8 kappa. It's very small. Okay. Here the system parameter is we choose the system parameter for those that can be realized experimentally. This value. So by this setup, we can determine the GM, the single photon optomechanical constant, to the level to the very fine level, very refined level. For that, if the G kappa equal to 1 million, for example, if kappa is chosen like 100 million, this small g can be determined up to 1 Hertz, to the order of 1 Hertz, much higher than the previous experiment. Okay. The reason that this sudden transition can be detected very easily, just like these two curves. The huge amount of the photon number in the order of 10 to the 11 by detection, by any type of, I think by the available type of the photon detector, this difference can be found immediately. That's it. Okay. Here, this type of research was published. Okay.
Sorry, we have like 5 minutes left because I want to leave
time
for questions.
Okay.
Yes.
Okay.
Thank you.
Okay. It's almost finished. Okay. Okay. For this part of research was published in this year, in this paper. Okay. Sorry. In this paper, it's just recently published as a letter to physical review research. Okay. 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 So I stop this talk. I give a summary. Okay. In this talk, we check 2 dynamic phenomena. One of them is about the mechanical motion, mechanical oscillation frozen by 2 driving field with matched frequency. We saw that the mechanical oscillation of one mirror, a macroscopic object, can be quantized. Also, the evolution to the high level is very sensitive to initial condition. This is something quite unexpected. The second dynamic scenario we have discussed is about a sudden transition in a coupled system. It is actually a dynamic version of catastrophic bifurcation in nature. It's a sudden change, but by just tuning the external parameter, it's what sudden change. The system behavior changes totally suddenly. Okay, so there's a very useful application for that such kind of sudden change to precise measurement. Okay, for both of these systems, we are just dealing with some very simple system with few degree system, with very few degree of freedom. The first system has only 4 degrees of freedom. The second one with only 6 degrees of freedom. But we still saw a lot of interesting phenomena existing in such simple systems. Okay, thank you for all. In the talk, the end.
Oh,
okay, okay. Any question?
Yes, I'm gonna allow to everybody to unmute themselves. Sorry. So if you have any questions, you can unmute yourself and ask the question directly. Guys, if you have any question, and if you are shy and don't want to ask in English, you can ask the question in Spanish and I can translate. So
yeah, you can translate. Maybe I can understand some Espanol.
Yeah, he's living in Chile, so he's already familiar with the language. Guys, anybody questions? Somebody? Anybody? Nope. Okay. So, well, thank you so much, Bing, for being here. It was really, really nice to see you again. And
me too.
We're gonna invite you. We will be having these seminars, so we will invite you for the next one. That is another guest. And thank you, everybody out there. I'm gonna switch to Spanish because I have to give some announcements.
Okay.
So,
okay.
Yeah, for the community. Entonces,
okay, I'm going to leave.
Muchachos.
Okay.
Okay, thank you so much, Bing.
Thank you. Have a good one. Bye.
Bye. A ver, hola muchachos, a todos los que participan en la división y en la red. Yo soy Gina. Les quería dar 2 anuncios que el día de mañana, entre el día de mañana y el viernes, y el lunes, voy a estar mandando 2 formularios. Uno es para que lo compartan a toda la gente que quiera participar tanto en las actividades de la división y de la red, estudiantes e investigadores, para que actualicen su información, correo, institución, etcétera, etcétera, porque la lista que tenemos ahorita parece que ya está un poco obsoleta. Y la segunda va a ser un formulario para que lo compartan entre los estudiantes de sus universidades, que tiene que ver con el diplomado que queremos introducir en la Iniciativa Mexicana de Tecnologías Cuánticas, y es el diplomado que estamos implementando. Ese va dirigido para los estudiantes. Entonces, les encargo mucho que participen con ambos formularios. Yo se los voy a estar mandando entre hoy y el lunes. No sé si tengan algún comentario más, preguntas para mí o algo más que quieran añadir. ¿No? Bueno, pues muchas gracias por haber estado aquí a todos y nos vemos la siguiente semana. Yo les mando toda la información. Nos vemos, muchachos. Bye, bye.